Not very exciting. Thank you, thank you, thank you. It's the 25th. Oh my God. I still can't believe next week is April. That's just crazy to me. All right, you guys, let's do this. Let's get started now. So we are doing section 11.7. 11.6 is more vector stuff, but it's more non-calculus vector stuff. We don't need to do it. It won't be on anything that you need to know in this class. But this is calculus of vector valued functions. This is actually one of my least favorite days, to be honest. I hate that we end on this day. And it's one of my least favorite days because we don't really get into the, deep into this topic. And so it almost seems kind of silly and pointless, honestly, because we don't get that deep into it. And it's so similar when we start getting into the actual calculus of it, it's actually so similar to parametric. It's like, what's the point? But, well, it is on the AP. But the good news is, probably know a lot of this that you need to know for the AP. So, but what is a vector valued function? That's a good question. I'm glad you guys asked that. Definition of a vector valued function. Well, duh. It's a function with whose values are vectors. There, that's clear as mud, right? But that's really what it is. It'll look something like this, R of t. So it is vectors, but it is a function of something, typically time. So typically we use t. T or theta are the common ones. There's two ways to write a vector valued function. One looks like this. So it's a linear combination of our standard vectors I and j, except the coefficients are functions of t. Or another common notation Following exactly what we did last class with the different kinds of notation, another common notation then is where we just put the horizontal component and the vertical component like this. Again, the horizontal and vertical components are just functions of time. So R of t is a vector valued function where the component functions f of t and g of t are real valued functions of the parameter t. Parameter t. And there you go. So exciting. So you can see that if we, oh, yes, go ahead. It's not. This is why it's kind of boring, but it's not. In fact, when we get to graphing these things, the idea behind the graph is different, but it seems like the result is the same. I mean, there are some differences when you start getting deeper into it, but we're just not going to, which is why it's very boring. I'm sorry. But let's talk about graphs. Graphs of a vector valued function are the curve traced out by the terminal point of the position vector R of t. So what does that mean? I don't know. Let's look at an example. We'll figure it out together. So for example, let's look at a very simple one. Let's look at this guy. The horizontal component is going to be cosine t. The vertical component is going to be sine t. Now, if these were parametric equations for a parametric curve, anybody remember what this is going to look like? It's going to look like a circle. So let's see what it ends up looking like when we start bringing vectors into the equation. Bad joke. So I'm going to go ahead, put a graph here. I don't know. It's going to turn out we won't need that much. So I'm going to make my scale kind of big like this. Otherwise, the graph would be really small. Yeah. Okay, so let's just pick some values and kind of see what's happening. So we'll have t, and then we'll put r of t. And we'll look at these guys. So when t is 0, what's the vector r of t? What are the horizontal and vertical components for r of t going to be? 1, 0. And what about pi over 4. Godzilla. Oh my goodness. Godzilla, 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 Godzilla. All right. At t equals pi over 2. 0, 1. I'm not going to go all the way to 2 pi, but 3 pi over 4. Sorry. What about 3 pi over 4? Yes. And pi. We'll see if we can get an idea of what's happening just stopping at pi. If we have to go further, we'll go further. But at pi, what are the coordinates? All right. Or the components, I should say. Okay, so we have 5 vectors. Let's see if we can figure this out. So the first vector, 1, 0. Now, for vector valued functions, we saw last class that you can actually draw the vector anywhere in the coordinate plane you want. When we're actually plotting vector valued functions, we're going to have the initial point for all the vectors start at the origin. So starting at the origin, going 1 unit in the horizontal component, but 0 units in the vertical component, the vector ends up, I don't know if you could tell what I drew, but it's that horizontal, green horizontal vector right there on the positive x-axis. So that's that guy. Root 2 over 2, root 2 over 2. Let's kind of eyeball this. Anybody remember what the value approximately is for root 2 over 2? Is it a decimal that you ever got to know? What's root 2 approximately? 1.4. So what's half of 1.4? 0.7. It's actually like 0.707, blah, blah, blah. 0.7, though, is good enough. Kind of eyeball it. I don't know. How about right there? It's probably a little too far. Oh well, it's good enough. All right, the next vector, starting from the origin, 0, 0 units in the horizontal direction, but 1 unit in the vertical direction puts me up here. Negative root 2 over 2, root 2 over 2 will put me right here. Negative 1, 0 puts me right there, and so on and so on and so on. So we can see how this is making a nice, we can kind of see the circle that's similar to what we see on parametric curves. So if we kept going, yes, indeedy, we're going to go around the entire circle like this. But this is not the actual function. This is not the vector value function. Because if you read, I still have it on the screen. They are traced out by the terminal point. All we actually care about is the terminal point. So the terminal point for the vector went from here, and I think we can see it's going to hit all the stuff in between. So it's going to go from here to here to here to here. So as far as the terminal points go, what shape do the terminal points trace out? A circle. A whole lot like a parametric curve, huh? In fact, it's exactly the same kind of thing as a parametric curve. Oh, actually, I think my estimation wasn't too far off. Wow, makes a nice circle. I'll take it. So the pink circle is the graph of the vector valued function. R of t. Yes. Say that again. How do you know? You got it? Okay. Yes. So this is where, I mean, there's a whole lot more applications that we just don't get into, but we're sort of going to get into, but not enough to really fully understand them. But we're going to look at tangent vectors to this curve and what the tangent vector sort of kind of means in a way. And um, uh, but there, well, but we're going to look at it because then the tangent vector, so we have a tangent line, but the tangent vector will have not only a direction like the tangent line, but will also have a magnitude. So depending on the problem, that magnitude can have some meanings that we don't get with just a parametric curve and a tangent line. So that's what I mean by there's these deeper meanings that we're just not going to get into. So it all seems like silly. Yep. So we're just going to go with it. One thing that's kind of cool. So a lot of times when so it's really, it's always kind of puzzled me actually why College Board puts vector valued functions in it's usually like a Calc 3 topic when you start getting into multivariate calculus. And then you start, because these actually can start tracing out some really cool curves, like saddles and other things. I forget what they're called. There's like, imagine if you took like a pizza crust dough and you're starting to flatten out, but then when you put your hand in, how it kind of does that thing, you'll start looking at shapes like that. We could take a simple one like this. If we put a third dimension, if I had a way to draw 3 dimensions for you. So we know 2 dimensions, like if I'm looking down where the 2 dimensions is flat, this is just making a circle. Well, if I introduce a third component that would move in the vertical direction, and for this particular one, if I just made it t, what's going to start happening is that circle will start moving off the page and it creates a helix, which is kind of cool. So there's like some cool things that start happening when you get into multivariate. So I think this is at the tail end of BC because it's like your little preview for what you're seeing in the next level of calc and multivariate, calc 3, whatever your college calls it. But it's just a weird thing. Anyway, any questions though about this idea of the curve is traced out by the terminal point? All right. So you can actually take limits and derivatives and integrals of these vector valued functions. But guess what? Like you've done before. You can tell I'm really jazzed about this topic. Sorry. It's one of those things I have trouble getting enthusiastic about. Polar, that's cool. Vector valued functions, this stuff. Yeah. Multivariate. From what I remember, I actually haven't done multivariate. You know how long it's been since I've done multivariate calculus? 33 years. Since very, 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 very little. Yeah, I have to admit. Limits, derivatives, and integrals. Oh my. Oh, vector valued functions. We're just going to do an example because they're really intuitive. Kind of a pain sometimes. Squeeze it in there. So for example, if I said find the limit as t approaches 0 of this vector valued function, 1 over t plus 1 e to the t minus 1 over t. Anybody have a gut feeling what the answer to this is going to be? So, with all three of these, with all three of these, limits, derivatives, and integrals, we call it, it's done component wise, meaning you do the components individually. So for instance, if we look at just the horizontal component, the limit as t approaches 0 of 1 over t plus 1. What does that equal? Yeah. That's 1. Yeah. Now, oh, that was the wrong color. The limit as t approaches 0 of e to the t minus 1 over t, what does that equal? What do you get when you directly substitute? 0 over 0, which is, yeah, we got to use L'Hopital's rule. It's indeterminate. So we don't know yet. L'Hopital's rule applies. So the derivative of the top is just e to the t. The derivative of the bottom is just 1. Can we do the limit now? What is the limit? Okay. So that's the answer. So it's like 2 problems in what? 2 problems for the price of 1. Yeah. Yeah. All right, any questions on that example? All right. What about this example then? What about if I told you that r of t is 7 minus t for root t, and I wanted you to find r prime of t. Can you do that? Yes. Two to the negative root 2? Wait, what? No. What do you guys think? Yes. So you literally just take the derivative of each component individually. Yes. All right. How about integration? What about if I asked you to evaluate the integral from 0 to 1 of t e to the negative t squared I plus t natural log of t squared plus 1 j. Oh yeah, I put the limits there. I know, right? Looks kind of badass, doesn't it? So we're going to do it component-wise still. We're still going to break it up into 2 separate problems. You can try to show your work all at once. Kind of honestly depends how complicated the problem is, if I split it up or not. But we're going to look at just the horizontal component. How does that look? Does that look better? Ah. And you're going to get that answer. And then you're going to look at the vertical component. And you're going to get that answer. And then you're going to put that together in your final answer as your coefficients, as your component vectors for I and j. So, yeah, go ahead and do it. I'll do it too. I won't pause, but try to do it on your own without looking. Oh boy. How are we going to do that second one? Anybody have an idea? Perfect. That's exactly it. Oh, this will be a perfect review of integration by parts then. Yeah, gotta do it sometime. Tear the band-aid off. Do it right now. All right, so if we do U sub on the second one, we get this. I'll walk you through integration by parts if you're still having trouble. Do you guys remember the formula for integration by parts? So it's the integral, well, like, what would the left-hand side be? The integral of what equals all that other stuff? Nice. Integral of u dv, and then I heard you give me this other part, equals uv minus the integral of v du. Now, the only thing is, we're already using u. So I could have, instead with u substitution, I could have used w, or since I've already written it with u, I'm going to make it w and v instead of u and v. And change all of these u's to a w, because they are not the same u that we had above. And then I think I heard somebody saying Liate. Yeah, Liate is going to help you. It's a guideline. It's not a hard, fast rule that always works 100% of the time, but it works the majority of the time. Go through the letters in Liate, and the first thing you come across in your integral, that's what you're going to let equal u. Try that out. So what's the L stand for in Liate? Do we have a log? All right. But we're using, instead of u, we are using w. So I'm going to let w equal the natural log of u. Actually, wish I had a little more room. I'm going to move this over. Ah, not that. If w equals a natural log of u, then what is dw equal? Du. Don't forget those du's and dw's and dv's and all that other d stuff. All right, what does dv equal? Du. So that means v was u. So we assign the natural log of u to w and the du to dv. And then from those things, you find these other two things, and then you literally just plug into the formula. So any questions just finding that? Because now when we plug, this is an easy one. Some of them still you have to do a little bit of work. This is one where the integration is really easy. So if I start from the beginning of this formula, you'll see it gives me the same integral. W is the natural log of u. dv is du, and that is the integral we're trying to evaluate. wv is u natural log u. And then it's minus the integral of v dw, but v dw, the u and 1 over u cancel out. So we're just left with du. So the integral of the natural log of u du is u natural log u minus u plus c. So the natural log function is one of those, if you just have a natural log and nothing else, it's got to be an integration by parts problem. So any questions how we got that? Because then we're going to go back to the pink stuff. All right. So that means 1/2 the integral of the natural log of u du is 1/2 times u natural log u minus u. And I'm actually going to leave it like that. Normally we'd have the plus c. I'm going to put my limits in. I just do it from here. But what do I have to do to my limits first? Change them, because my limits were in terms of t. So I'm going to go back up here for a second. My lower limit was 0. If t is 0, what is u equal? Okay, so 1's going to be my lower limit. And if t was 1, what is u equal? 2. So I'm going to go from 1 to 2. 1 to 2. 1 to 2. So we have 2 natural log 2 minus 2 minus natural log of 1 minus 1. Natural log of 1 is 0, so minus the negative 1 is going to be 1. So we're just going to have, whoops, 2 natural log of 2 minus 1. If we distribute that 1/2, get the natural log of 2 minus 1/2. Whew. Any questions about that? What were we doing again? Yeah. What was the problem again? Oh, yeah, the integral of vector value. Got it. So there's our horizontal component, and we just found the vertical component. We put it together, and that's our answer. I know, it's crazy. Since the original problem was in terms of I and j, we'll put our answer in terms of I and j. Oh, is that going to be your question? I mean, you don't have to, but I'm just going to. So 1/2 minus 1 over 2e. And then natural log of 2 minus 1/2 j. Ta-da! So it's just as easy as or as hard as the actual limits, derivatives, or integrals are. Yes. No. Nah. Yes, it. Okay. Any other questions? But wait, there's more. Okay. Does anybody need this at all? Okay. My tummy's grumbling today. What's for lunch? Ooh, nice. Cereal with milk? I'm sorry. But do you get at least milk with your cereal? Do you at least get milk with your cereal? But you don't know if you're gonna? Okay. When I was a kid, so there's like Count Chocula and Frankenberry. There's also Blueberry, which is hard to find. So Blueberry with the marshmallows. You'd have blueberry cereal with strawberry milk. Talk about sugar overload. Oh, good. Back in the 80s, we didn't care about sugar. Put sugar in everything. Jolt Cola. Jolt Cola, which I'm proud to say was bottled in my hometown. I'm pretty sure Jolt Cola is no longer bottled. Jolt Cola, with the tagline, like the way they advertised it, because they were proud of it, it was like something like twice the sugar, twice the caffeine. I don't know, same sugar, twice the caffeine. I know I remember twice the caffeine. I mean, the whole point was sugar and caffeine in this cola. Yes! My brother and I got like a liter bottle and we shared it between the two of us. And then we promptly passed out on the bed because we never, caffeine doesn't affect us. But yeah, Jolt Cola. Oh, all right. What's next? I don't know. This looks fun. Vector parametrization of a tangent line to a curve at t equals t naught. Not. You may think it's funny to be kissing with your honey when you feel your nose is runny, but it's not. Anyway. All right. It's a vector parametrization, so we're going to make a vector out of this tangent line. And the vector is simply r t naught plus t times r prime t naught, where the tangent vector r prime t naught is a direction vector of the tangent line. Wait, what? If you think about rectangular coordinates, when you guys did the tangent line, it's really the same kind of format. So if we compare to tangent lines, excuse me, in rectangular coordinates, something you guys did way back at the beginning when you first learned about derivatives, back in AB, if you can remember those days. Remember when you were so young? Oh. But if I asked you like to find the tangent line to y equals f of x at the point x naught, y naught, why not? Well, that's where we learned, or not learned, but that's where we started using point slope form a lot. So the tangent line in point slope form, y minus, you pick a point on the curve, but we already know a point on the curve, x naught, y naught. So y minus y naught is m times x minus x naught. But let's actually think about what's going on here. Our m is just our derivative. Our slope, or sorry, wait, yeah, our m is just a, Anyway, I said one thing, but was writing another. So I'm gonna, if I solve for y, we put the y naught on the other side. But slope is just the derivative, but it's, for this problem specifically, the derivative evaluated at x naught. And then we have the x minus x naught. But y naught is the same thing as just f evaluated at x naught. Which is really the same thing, basically, that we have up here. That's where the line, that equation up at the very top of the screen is. So y is our tangent line. L is a parameterization of the tangent line. We have the position vector, r of t naught. This is just f of x naught. And then it's r prime of t naught. We have f prime of x naught. And then it's just multiplied by your variable. This is multiplied by the variable. But it's the same thing. So you can remember it that way. It's just the same thing as what you guys have been doing. Hey, come back. All right. So let's look at an example here. We just have 2 examples and then we'll be done. Example. Plot r of t equals cosine t sine t. We did that at the beginning. We know how to do that. Together with its tangent line. Oh, sorry, tangent vector. My bad. Tangent vectors at t equals pi over 4 and t equals 3 pi over 2. So we've got the tangent vectors, but then we have this where we're going to find a parameterization of the tangent line at t equals 4. So we'll see kind of like a little bit of a difference between the tangent vectors and the parameterization of the tangent line. So first I'm going to go ahead and draw this. This is the same circle we drew at the very beginning, so we know it's a circle with a radius of 1 centered at the origin. I am going to draw it kind of big like I did before though, so we have enough space to show what's going on. I don't know how big I'm going to make it. Looks like I'm going to let every 3 again. Every 3 squares will be equal to 1. That'll be good enough. All right, so there's r of t. So then, whoops, don't want to use blue. Let's find those tangent vectors. Eek. At t equals pi over 4. Tangent should make us think about derivative. We are going to find the derivative. So what is the derivative of r of t? Negative sine, cosine. So then if we evaluate it, whoops, at pi over 4, we know we're going to get negative root 2 over 2 root 2 over 2. what does this mean when we draw the tangent vector? So what we're going to do, imagine the vector itself. Since we're using t equals pi over 4, then if we went back to the original, r of pi over 4 is going to be root 2 over 2 root 2 over 2. So that vector right there is the location vector for r of pi over 4. Not r prime, but r. And I probably can't see what I wrote. I just wrote r of pi over 4. So that's the location vector. We take its terminal point, and that's where we're going to draw the tangent vector. So this tangent vector says from this initial point, go negative root 2 over 2 units in the horizontal direction, root 2 over 2 units in the vertical direction. So again, just kind of eyeballing it, we're going to go negative 0.7, 0.7 from that initial point. So that would actually put us pretty much on there. We could probably use some trick to save it. 3 squares is going to be 1. That actually might put us right on the axis. I'm not sure, but I think. So we go the same up. And sure enough, it looks tangent. Yes.
So, alright, so by using this calculation, that blue line, the blue vector you just drew is r prime at pi over 4, and you've just drawn it. Okay, alright, so vector you draw anyway, right?
Yes.
And so you've just drawn it starting like the tail at the head of the, and then it lines up with the.
I think it does in this case, just eyeballing the units, but it won't always. But one thing I do want to clarify, so with vector valued functions, so you did say like with vectors we can draw them anywhere. With vector valued functions, we draw the location vectors always from the origin, and that will tell us where the terminal point is that traces out the curve. And then when you draw tangent vectors, the initial point is always at the head of the location vector that it corresponds to. Any questions about that? And then, again, I'm not going to get into it, but you can kind of see, oh, wait, we've got normal vectors there. Oh, wait, there might be some physics stuff going on. And there is, but we don't care about that. Yes? No. The length of r prime is just going to be based on its new. Actually, let's find the other one. So let's do at t equals 3 pi over 2. We already have r prime from above, so I'm just going to go ahead and jump into r prime of 3 pi over 2. If you plug in 3 pi over 2 into this vector right here, r prime of t, what's negative sine of 3 pi over 2? Yeah, it's going to be 1. And then cosine of 3 pi over 2? 0. So, with this guy, so first if we draw r of 3 pi over 2, r of 3 pi over 2 is going to be at 0, negative 1. So it's going to be down here. So the vector itself, that's r of 3 pi over 2. So there's its terminal point. So then this terminal point going 1 unit in the horizontal direction, 0 units in the vertical direction. This one ends up giving us this vector. It's just coincidence on this one because we have a circle. I'm pretty sure, if I remember your homework right, you'll see where, yeah, it's not the same. That's 3 pi over 2. So we have the location vector, which will give us the initial point for the tangent vector, and then from there you draw the tangent vector. So that's answering the first part. So we plotted the graph along with those two tangent vectors. Now let's find the parametrization of the tangent line at t equals 4. So any questions so far? Yes. Oh, wait, so you're saying like negative cosine t sine t? Yeah, I think so on this. I don't know if that's true all the time. Could be, but I don't know. I'd have to think more about it. Yeah, that's why I'm not sure if it's true all the time. Well, I mean, you could, I mean, we'd have to plot some points. I mean, we could just see real quick if we go back up. Where did we have this guy? So let's, if we made all these, the horizontal components negative. So starting at negative 1, 0. Yeah, so you are going this way now. If it was if all of these, the horizontal components were negative. But yeah, I don't know if that's always true for just a generic one. There's no symmetry in this circle, so that could be why it's happening. Any other questions? Okay. Yeah, I think I have enough room. So let's do the parametrization of the line. Parametrization. It's just a fun word to say. Parametrization of the tangent line. At t equals 4. So let's write down the equation, just the general equation first, and then we'll plug in, and you'll see it actually. So remember the equation that I gave you was this. Then t is going to remain a variable, but t naught is where we're going to plug in our value of 4. I don't want 4 though. I don't think I meant 4, because that's just going to be a weird value. Let's do pi over 4. I wrote down 4. I think I wanted pi over 4. I'm going to change the problem. All right, so can't write. We're going to plug in pi over 4. Now, we have our vectors up here. So as far as r goes, we're going to plug pi over 4 into that vector at the top line. That's just going to be root 2 over 2, root 2 over 2. Root 2 over 2, root 2 over 2. But then, we already found r prime of pi over 4. That was right here. So that is negative root 2 over 2, root 2 over 2. So any questions where I'm getting this from? Yeah. Yeah, I mean, we have it right now, so yes. But the I mean, you'd have to still get the parameterization, meaning the horizontal and vertical component. So could we graph it? Yeah. Yeah, but I mean, it's only because our numbers are friendly. What if you had some ugly numbers and you still had to write the actual components? Well, if it's in trig, but what if it's not? True, but again, who knows what your numbers are going to be? Okay, so then we got this. So if we distributed the t into here, scalar multiplication, and then also added the corresponding horizontal and vertical components, then we just wind up with root 2 over 2 minus root 2 over 2t for the horizontal component, and root 2 over 2 plus root 2 over 2t for the vertical component. And voila, we have it. What does this mean? I don't know. Actually, I'm just kidding. But any questions how I found it? Next thing is we're going to see what it means. And remember, they're calling it, even though we're dealing with vectors, even the name is recognizing how this is just like doing parametric equations, because we have found the parameterization of this tangent line. Think of these as a set of parametric equations for a curve. So you don't have to do this part, but I'm just trying to like show you what it means. I am going to go to a new page for this. We basically have one function. If we think of it in terms of parametric equations, one function, and actually I'm just going to write it as x, for our x of t, which is root 2 over 2 minus root 2 over 2t, and our other equation for y, which is root 2 over 2 plus root 2 over 2t. Let's see what it looks like if we eliminate the parameter and write it in terms of just x and y. How do we do that again? Dylan? No. Sorry, I saw his hand move. One way you can do it is just take one of the equations, solve for x or y, depending which equation, and or solve for t, and then plug into the other equation. They're both pretty much the same equation. So let's just take x. If I multiply both sides by 2, we get 2x equals root 2 minus root 2t. 2x, well, whatever, I started at 2x minus root 2 equals negative root 2t. So if we solve for t, it's root 2 minus 2x over root 2. So we're eliminating the parameter. And then if we plug into our equation for y, oh, geez, this is going to get ugly, huh? We get root 2 over 2 plus root 2 over 2 times t, which now we know is root 2 minus 2x over root 2. Oh, good Lord. That looks ugly. Let's see what happens when we simplify this down. But do you see what I'm doing? Just plugging in. So let's distribute that fraction there. The numerator, that's just going to become 2 minus 2 root 2x. The denominator is just 2 root 2. Looks like 2's are going to cancel out. So we get root 2 over 2 plus 1 minus root 2x over root 2, which I'm going to kind of do two things at once. I'm going to split the fraction up. So we'll have 1 over root 2, but that's the same thing as root 2 over 2. Minus root 2 over x, or root 2x over root 2. So the root 2's cancel. Oh, this is just root 2 minus x. So the parametrization of the tangent line would give us this line in rectangular coordinates. Let's go back to our graph for a second. Remember, root 2 is about 1.4. That's our y-intercept. Slope of negative 1. Here was the tangent vector. Wow. If this is 1, not bad. This should have hit about, it should have hit exactly at root 2. My graph's not horrible. It does have a slope of negative 1 though. So it's a parametrization of the line that would go through that vector. That's all it means. All you have to know is how to find it. Yes. So if you think about what slope means, slope is just a change in the, it's rise over run. And we have our rise as the vertical component. We have our run as the horizontal component. Yeah. All right. One more question, and this one's super easy. This is like the weirdest thing, but any questions about that? Yes. Yeah, and actually, I mean, this is also one of those things where technically we're doing the parameterization and we're doing vector values. So some people say, well, technically we should have these angle brackets, but you'll actually see because it's just like parameters, a lot of people just put parentheses like it's parametric equation. So. All right, last example, the path of a particle satisfies, there's only one particle, satisfies dr dt equals 1 minus 6 sine 3t 1/5 t. There's two parts to this guy. Find the particle's location. And velocity. This is the one that I wanted to be at t equals 4. If r of 0 equals 4, 1. Dun, dun, dun. So what are we going to do here? Anybody have an idea for either location or velocity? Yes. Yeah, but you're right. Yeah, so the r of t itself would give us the location vector, the position vector. Position vector gives us a location. That's why it's called position. We have the derivative, so we have to integrate. And then when we integrate, we're going to get some c's. We have a value to plug in to find the value of those c's. Ah, I know, right? So let's do that. Very exciting. So for the location, we're first going to integrate 1 minus 6 sine 3t 1/5 t. I think we can do this without splitting it up. So the antiderivative is going to be 1, no, it's going to be t minus, is it minus? No, it's going to be plus 2 cosine 3t plus 1 value of c, which we'll call c1, and then 1/10 t squared plus a different arbitrary constant, we'll call c2. And then we have a vector for 1 that we can plug in to find the value of c. So any questions what I did right there? So the position vector is 4, 1 when t equals 0. So I'm going to let all those t's equal 0. We get 0 plus 2 plus c1, 0 plus c2. So what does c1 equal? What's c2? So now we have r of t. Hey! R of t is just t plus 2 cosine 3t plus 2, 1/10 t squared plus 1. We evaluated 4, and we get our answer. I'm going to get decimals. But now make sure your calculator's back in radian mode. Last night's homework, degree mode, back in radian. 4 plus 2 cosine 12 plus 2. That's about 7.687. 2.6. So there's your location. Remember, it's still a vector, but then the terminal point will give you the location of the particle. How am I going to find the velocity at t equals 4? Yeah. No. It's actually going to be a vector itself. Yep. But in general, if we had a function for position, what did we do to position to get velocity? Derive. And they've already told us what their derivative is. So all we actually have to do is let t equal 4. So we're going to take dr dt and evaluate at t equals 4, and that will give us a velocity vector. What was it? 1 minus 6 sine 3t. So 1 minus 6 sine 12. And then 1/5 times 4. So about 4.219.8. There's your velocity vector. Done. We're done. Any questions? Just kind of go with it. All right, then we're done. Sorry, I was gonna pause the video. Ah! Can I pause it this way? No shortcut. All right, fine. Math. Oh, you know what? I can pause this. Forgot. Math is beautiful. You are right.